Hi, and welcome back to this video series about Probability Theory, the Logic of Science by Edwin Jaynes. Last time we talked about the orthodox statistical methods as Jaynes presents them in chapter 16 of the book, and we got to an understanding of where those methods actually kind of work and give fairly reasonable results in a narrowly constrained set of problems. And this time what we're going to do is look at where those methods break down. Okay, so we're going to stray outside that well-behaved region and look at where the orthodox techniques are going to give us some absurd and kind of illogical results. This will be drawing some on chapter 17 of the book called Principles and Pathology of Orthodox Statistics, but only really the first couple sections of it. Okay, so Jaynes does some very long examples towards the end of the chapter that we're not going to get into, but they're very interesting. I encourage you to look through them. I'm also going to be drawing a little bit from material elsewhere in the book, and I'll try to indicate where that is as we go. Okay, so just to recap a little bit, last time we were talking about the orthodox statistical methods. We said that in the orthodox framework, really the big question is what is allowed to have a probability associated to it. Okay, so in the orthodox mindset, probability comes about because of randomness and sort of stochastic processes that you can observe over time, and therefore probability just has to do with randomness of the data and frequencies of occurrence of data of different values or of different character. So really, I think the essential kind of summary of the orthodox statistical program is to say, first of all, only the data are random. Data are kind of the only random thing. And what that means then in terms of hypothesis testing and parameter estimation or any kind of statistical program we want to undertake, everything has to be phrased in terms of probabilities of the data. Okay, so only the data are random, meaning only the data get probabilities assigned to them, or probability assignments, meaning frequencies of observance of different data. And so we can only ask questions that depend in some way on the probabilities of the data. So this leads us into what Jaynes calls the pre-data questions. Okay, so any question we want to ask, like how often will the data have a particular value, or how often will we draw a particular conclusion from the data, all these things we can do in the orthodox framework. What that means then in terms of, let's say, things like hypothesis testing, is that we have basically a limitation of the kinds of questions we can ask, and so the process of a hypothesis test has to follow kind of a particular template. Okay, so the basic steps of that are going to be, first of all, defining what would be called a model. Okay, and as part of that model, maybe the working hypothesis or parameter value or whatever it is that we're interested in testing, and thinking through then probabilities of the data under these different modeling assumptions. Okay, so we might have a model that says that the data are, let's say, normally distributed around some value, and the value might be a parameter in our hypothesis or in the sampling distribution, etc. We'll then think about summarizing the data by some single quantity, and that is usually going to be something like a test statistic or parameter estimator, or some kind of summary quantity that depends numerically on the data that we realize in some way. So maybe it's the mean of the data or some other number. This is going to be some function of the data, and as a consequence of our modeling assumptions, we're going to be able to compute things like the sampling distribution of this number f. Okay, so that will be basically answering the question, what's the probability that f lies in a certain region? We'll then specify some particular kind of special regions of that sampling distribution of f, which will be our what we'll call our rejection region. Let's just say that's R. And we'll usually set it up so that this is kind of an extreme region where it's sort of evidence against H0 in some sense, and we'll kind of pick it so that the probability, let's say, of f being in this region, conditional on this null hypothesis or this modeling assumption that we're making, is some small number, and for most purposes we'll take that number to be 0.05 or 5%. Okay, so this will be our 5% tail area, or our extreme values that together make up about 5% of the total distribution of f. Okay, so then the basic question is, all right, is the value that we actually observed from the data in this rejection region? Okay, so if when we actually do the experiment, we get a number that is somewhere out in this extreme region, then we reject the null hypothesis, and we say we reject it at the 5% level, okay, meaning it fell into the region of small probability defined by however significant we decided to make this test. And if it does not, then we say we fail to reject it, or we maybe say we accept the null hypothesis, or whatever it is. Okay, so usually the name of the game, the hardest part, is going to be in this step 2. Okay, so this kind of logical template will apply to all of the kinds of statistical questions we might want to ask about various modeling assumptions or various parameter values or null hypotheses, or however we define them. And it's just going to be a matter of choosing which test statistic we think kind of summarizes the data in such a way that we can test that thing. That test statistic may be some complicated function of the data. It may depend on the data in some kind of complex way. And our model might be fairly complex and might have lots of kind of moving parts to it. And so computing things like the sampling distribution of the statistic, or in particular kind of turning that around and saying, all right, what region is it that has a kind of 5% probability that we're going to take as indicative that something's wrong with this null hypothesis, finding that region, that's going to be the hard part. Okay, so if you read through, again, a standard kind of statistics textbook, you're going to find lots and lots of tests that basically follow this kind of template. So that's your t-test, your f-test, your ANOVA, your chi-squared test, Kolmogorov-Smirnov test for distribution, Anderson-Darling, Dickey-Fuller tests, et cetera, et cetera. Okay, so basically every kind of fancy and sophisticated statistical test is going to just be a different kind of test statistic based on testing a different model assumption or finding a different parameter value. Okay, so we know that there's some kind of logical problems with that, and we know that in particular because we've built up this logical program where we're able to talk about things like the probability of a hypothesis. Okay, so again, in the orthodox kind of presentation, the reason why this object distribution of f of d is so interesting is that it's the only kind of thing that's random, and it's therefore the only thing that you can ask probability questions about. Okay, but in the end, you want to really be asking about H0, so this procedure is not built in any way around saying, okay, the probability of the null hypothesis is small, therefore we reject it. Right? Because in the orthodox presentation, we don't have things like the probability of a null hypothesis. We can't assign probabilities to a hypothesis because those aren't random. Okay, so as Bayesians, that's what we'd like to do. We'd like to be able to say, actually, it's the probability of the null hypothesis we're interested in. We'll do some procedure and then reject it based on whether that probability is small or not. In the kind of orthodox presentation, we don't have that. What essentially we're trying to do is say, well, okay, based on H0, we get something, some observation, a statistic lying in some rejection region that's supposed to be very unlikely, therefore we're going to reject H0. And what people who use this procedure will kind of point to is the deductive version of this, which is what's called the reductio ad absurdum argument. Okay, so basically proof by contradiction. And the way that would work is you'd say, okay, if we had the assumption that P implies Q, so if we have as our kind of major premise that if P is true, then Q is true, and we know that we did not observe Q, or Q is impossible somehow, then we would conclude that not P is true. Okay, so basically just taking the contrapositive and doing a strong syllogism. Okay, now that's standard deductive logic, and that's totally sound. What we're kind of trying to say here is, well, if our hypothesis is true, then Q is kind of very unlikely, let's say. Okay, so not Q is very likely, so we did observe Q, right? So we kind of got something that was very unlikely, and we'd like to say, well, therefore, P is unlikely. Okay, and that would be kind of the probabilistic version of this. Unfortunately, that just doesn't really work out logically, and I think we as our kind of Bayesian logical program understand why that doesn't work out. People like Jordan Ellenberg in his book How Not to Be Wrong calls this the reductio ad unlikely, right? So basically somehow the version of reductio ad absurdum, but with probabilities. The reason that we know that it doesn't work out that way is that it all depends on what other possible hypotheses or minor premises or assumptions might have explained this unlikely data in some more likely way, right? Under what assumptions might the data have been more likely, and what would the prior probabilities of those things been, and then how does that kind of shake out in the Bayesian inference rule? Okay, so we've gone through that a few times. But anyway, that's where we know there's a kind of logical hole in this argument, and that's basically where we're going to probe and use it to show how this procedure will get to some kind of illogical answers. Okay, so to begin with then, let's consider a situation where even by orthodox kind of standards, we have a null hypothesis that should have a probability associated to it. Okay, so again, our kind of Bayesian logical program allows probabilities of hypothesis. Orthodoxians would usually say those things don't get probabilities because they're not random, and therefore the prior probability of the hypothesis is just not an ingredient of this procedure at any point. But let's try to set things up so that actually even an orthodox statistician would agree that our null hypothesis is something that should have a probability associated to it. Okay, and the way we can do that is by defining our null hypothesis in terms of a random sample. Right? So let's say that we have the situation of we have a population of people. In that population of people, there are some people that have a particular disease, and that disease has a 1% incidence rate. Okay, so by assumption, 1% of the population has whatever this condition is that we're talking about. All right, we then pick a person at random from the population, meaning we do a sample without replacement one time, and we do it in such a way that which person we get should be independent in some sense from whether that person has the disease or not. Okay, so we use a random number generator and we look this person up in the phone book or whatever, and we pull them out. We then want to ask the question, all right, let's define our null hypothesis to be that this person, let's just say is a he, doesn't have the disease. Okay, so right away you can see that we're in kind of an interesting situation where our null hypothesis is there's kind of nothing going on, this person doesn't have whatever effect we're going to be testing for, but even by orthodox standards, we can start thinking about the prior probabilities of that before we do any kind of testing or et cetera. Okay, so this is really kind of where this should start to get orthodox statistician's attention. Let's say that we then do a test, okay, a blood test or whatever kind of test, and the outcome of that test is either going to be a yes or a no. Okay, so it either tests positive or it tests negative. And let's just assume that the probabilities of these things under the null hypothesis work out to be like this. So let's say the probability of getting a yes result under the assumption that he does have the disease. Okay, so H0 is that he doesn't have the disease, not H0 is that he does have the disease. Let's say the probability of getting a positive result if he does have the disease is 100%. Okay, so there's no such thing as a false negative in this setup. And let's assume further that the probability that he tests positive if he does not have the disease is this 5% number. Okay, this 5% small number, which is basically our false positive rate in this setup. Okay, so now our assumption is we do this test and that we get a yes result. Okay, so it seems like, according to this kind of orthodox template, that this would mean that we should reject the null hypothesis, right? One way to think about that is that we're basically defining a test statistic that is just a binary variable. It takes the value either y or n. And the probabilities of it doing that under the null hypothesis, the probability of it being a y is 5%. So our kind of rejection region for this binary test statistic is just the value y, and we have set it up so that that's kind of evidence against the null hypothesis to the tune of this kind of magical 5% cutoff point that we would normally use for an orthodox statistical test. Now, if you wanted to, I think you could reframe this in terms of like testing the quantity in his blood sample of some pathogen or antibody or something, and then having a kind of distribution of that and cutting it off at some point and saying that's our threshold. Okay, for this example, it doesn't matter. We're just going to take this as a kind of binary variable. Okay, and it seems like, yes, according to the orthodox program, we have our null hypothesis, we have our test statistic, we've defined our rejection region with a small probability under the null hypothesis, and we got a test statistic in that region. So we should reject the null hypothesis. We should basically tell this guy, according to our best statistical procedures, it is the case that we have concluded that you have this disease. We've rejected the claim that you don't have the disease at the 5% level, at the kind of same publication standard that all medical and social science journals adhere to, and it's our best procedure that we know how to do. Okay. Problem with that is that we haven't included at any point this incidence rate and the prior probability of the hypothesis. Okay, so let's take a look at how that would actually play out if we did this the Bayesian way. Okay, and we know how to make a posterior probability assignment to this idea that he has the disease. Okay, so how would that work? Well, we know as Bayesians, right, what we're really interested in is the probability of H0 given this positive test result. And let's go ahead and throw in some background information because we want to keep track of that. Okay, background information is basically everything that gives us these sampling probabilities, etc. This is really what we're interested in, and we know how to compute it. We know that it's like the prior probability times a ratio, which is the sampling distribution under H0 divided by the sampling distribution not conditional on the hypothesis. Okay, this is our normal Bayesian inferential rule. This thing is going to be really the hard part, and we're going to actually just attack that by decomposing it, okay, in the normal way, as a sum of the probability conditional on H0 times probability of H0 plus probability conditional on not H0 times probability of not H0. Okay, and here's where we actually get to use our assumptions about the incidence rate of the disease as well as these sampling distribution assumptions. Okay, so probability of y given h0 is here. That's our kind of false positive rate. We know what that is. It's 0.05. Probability of h0 is the incidence rate, or it's 1 minus the incidence rate of the disease. Okay, so h0 is the hypothesis that it doesn't have the disease. By assumption, 99% of people don't have the disease. So without doing any tests, this is what we would assign to the probability of h0, okay, prior to the data. Okay, so far so good. Probability of y given the negation of the hypothesis we said was 1, so we're assuming there are no possible false negatives in this test. So if he's got the disease, then he tests positive for it. And probability of not h0, we know that also because we know the incidence rate of the disease. Okay, so that's 0.01. Okay, and if you think back to the kind of Bayesian hypothesis testing that we did earlier, a few videos ago, we know that actually once we can compute this number broken down in this way, we are finished with the posterior probability assignment. It's just the relative proportion of each term in this series, or each term in this sum. So basically, probability of h0, given this positive test, is the relative proportion of this first term divided by the sum, and that works out to be 0.05 times 0.99 divided by whatever the sum is, 0.05, 0.99 plus 1 times 0.01, and if you do that calculation out, you'll get a number about 0.83. Okay, so in other words, 83% probability that he does not have the disease even after having tested positive for it. Okay, and if you think about that in terms of these numbers, it kind of makes sense that it should be about 0.83 because let's say the population is very large, and we assume that 1% of people, when they take the test, they're going to get a positive result because they actually have the disease. About 5% of the people, let's say, when they take the test, they're going to get a positive result just as a false positive. And so of the population of people who get that positive result, about 5/6 of them did not have the disease originally, so that's basically our posterior probability assignment for not having the disease. Okay, this discrepancy here, this conflict apparently between kind of what the Bayesian logical rule tells you, and this is the right answer based on this posterior probability calculation, what that tells you in terms of the high probability of false positives kind of overwhelming the true positives, meaning that actually a positive test for a very rare disease with any kind of decent false positive rate is not actually very convincing evidence of having the disease. That little bit of argumentation is usually called the base rate fallacy. Okay, so the base rate fallacy would be what the orthodoxian statistical procedure gave us, which was where we ignore this. Okay, ignoring the incidence rate of the disease and just saying, well, the test seems like it has a low false positive rate, therefore we should conclude that guy has the disease just because he tested positive. And really, I think if you want to criticize orthodox statistical methods, you can basically say, well, they admit the base rate fallacy. They don't use this prior probability anywhere, and therefore they're just kind of committing this fallacy over and over again. Okay, and I think what makes this particular example interesting is that nobody would disagree with the relevance of this information to the inference, even orthodox statisticians for whom this null hypothesis probably gets a probability, but other ones wouldn't. And I think that it naturally raises the question of which hypotheses allow probabilities and which ones don't. Okay. So that's one kind of extreme. At another extreme, where this prior probability kind of matters quite a lot to the orthodox statistical program, is to say, okay, let's take an example like, let's assume that we toss a die some large number of times, and let's just say that it's 10,000 times, okay, if we are interested in, let's say, the hypothesis that the die is a fair die, and whatever we kind of mean by fair, the usual sense, then our data probability under that hypothesis is 6 to the minus this large number, kind of no matter what the data is, right? So any particular sequence, let's just say the data is a sequence of rolls, any particular realized sequence that long has this probability where we take 6 to the minus number of dice rolls. Okay, if you write that out in terms of a probability or in terms of the log odd scale, that's about minus 77,815 decibels. Okay, so a very astronomically small probability of getting any particular sequence of dice rolls under this assumption that it's a fair die. All right, now let's consider the alternative hypothesis. It's called HS, which is the hypothesis that the data were predetermined. Okay, and what we mean by this is, let's say that we did this sequence of dice rolls, we sat there rolling this die over and over again, and then someone came along and said to us, oh, that die you are using, that's a trick die that actually has this kind of very peculiar property where anytime you roll it 10,000 times, you get that exact sequence that you got. Okay, seems a little bit funny, but I guess we should allow it as a possible claim or hypothesis. So the issue is, all right, let's think about this hypothesis HS being predetermined. And this is what Jaynes calls the sure thing hypothesis. Okay, so this comes up earlier in the book in chapter 6, and then makes a couple more appearances later on. All right, so someone makes this claim to us that actually it didn't matter in what way we tossed that die, it was going to come up with that particular sequence of 10,000 dice rolls because of some tricky property that the die has. If we think about testing the hypothesis, HS, based on the data, okay, and this is again in the kind of orthodox framework, the sampling probability of that data, given the assumption that it's a predetermined kind of tricky die, is 100%, is 1. Right? Because it's the assumption that the hypothesis makes it so that the data is certain. Okay, so if we do a statistical inference, or let's say we do an orthodox statistical test, we can never reject this hypothesis HS. Okay, we can kind of never get around the idea that the data were somehow predetermined from the beginning of time or whenever, because this hypothesis makes it so that the data have probability 1, so actually the probability of any estimator or any test statistic is also going to be 1 if it's consistent with what we observed. Okay, so that seems a little bit troubling, meaning that if we do maximum likelihood or we do statistical hypothesis testing in the orthodox framework, we'll never say that we're in our rejection region for this hypothesis. Okay. In the Bayesian program, actually, we can get around that because we'll say, well, okay, let's think about this hypothesis HS. We'll think about the probability of getting the data under HS. I'll throw in the background assumptions now because we're thinking like Bayesians. Maybe we'd agree that probability is 1, but the power of the data, right, how much we kind of infer from it, only depends on the sampling probability along with the prior probability of HS. Okay, so basically the argument here is, yes, it's true that the difference between this certain probability and this kind of very astronomically low probability under the hypothesis that it's fair, that's a very large difference, and so each realization of 10,000 dice rolls is evidence to this degree, okay, in favor of this hypothesis, maybe over this one or over any other kind of suitably chosen hypothesis. If it is the case that we still don't believe it after having done the experiment, it must be that our prior probability for HS is something less than this, and it must be less than, well, this very small number minus 77,000 decibels. Okay, how can it be that we have such a low prior probability for it? Well, for one thing, we don't really believe in predestination, so that's maybe a personal orientation. But furthermore, there are many other possible sure thing hypotheses that would explain different sequences of dice rolls, right? So the reason we have such a low prior probability assignment to this particular sure thing hypothesis is that there are other ones, right? There are other sure thing hypotheses, and actually we know how many there are because we could write out or define a sure thing hypothesis for every possible sequence of dice rolls and say actually that sequence was predestined and no other sequences were possible. Okay, and so at least there are something like 6 to the n other possible sure thing hypotheses. We have no way to prefer one over the other. Okay, so in the Bayesian terms we'd be indifferent to them, so that means that at the very most we have probability of 6 to the minus n for each one. And that means that it's reasonable that we wouldn't reject that, we wouldn't accept that hypothesis necessarily given this experiment. Okay, so that's basically the Bayesian way around this problem, that for orthodox statistics you have no way around, because you can only talk about sampling probabilities under the hypothesis, and those are all going to be 1. Okay. So those are a couple of the kind of logical extremes of ignoring the effect of the prior probability in doing a hypothesis test. The whole kind of program of orthodox statistics really comes back to this question of what other data might you have gotten, right? So in this case, there's no other data you could have gotten. Depending on the modeling assumptions in the null hypothesis, you may have different allowable sets of other data you might have gotten, and you're having to define test statistics based on their behavior over these other possible data realizations. Okay, so another twist on this, where that kind of gets you into trouble, is to think about what's called the problem of optional stopping. Okay, so Jaynes mentions this again earlier in the book, I think in chapter 6, but it kind of comes back here in critiquing the orthodox school. So basically, the idea with optional stopping is that what conclusions we make from an orthodox statistical test might depend on some way depend on the design of the experiment that generated the data, and under what conditions that experiment was terminated. Okay, so the example that we'll talk about is, let's say that Adam is performing an experiment, and the experiment involves a sequence of trials, okay, of some apparatus, whatever it is, a sequence of those trials that can either result in a good or a bad outcome. Okay, so each time he does a procedure, he gets a good or a bad outcome. Okay, he's doing this experiment somewhere in a lab. And let's say that he writes up his procedure, and his notes for kind of what he did just say something very terse, like 12 trials, 3 good results. And the full data set he records as, let's say it's the sequence, it doesn't really matter, maybe it's 3 bads, a good, and then 2 bads, same again, and then bad, bad, good. Okay. So here we got our 3 good successful trials out of a total of 12, and the notes just say, I did 12, I got 3 good ones. Okay, so now 2 other scientists are going to pick up that data set and try to do some analysis on it, try to do some hypothesis testing. Okay, so Bill and Charlotte, okay, 2 other scientists, are interested in the question, is it the case that the probability of getting a good result is a half? Okay, so basically are good and bad results of this experimental setup equally probable, and that's their null hypothesis. Okay, really what they like to say is that good results are less probable. Okay, so we're kind of want to reject this in the extreme of there being a low good fraction. But the null hypothesis is that actually these things are just random, and so good and bad results are equally probable, and that probability therefore is a half. And let's just say that they both agree that the trials are independent of each other. Okay, so whatever probabilities they're going to come up with, we'll use independence of the trials. Okay, so Bill, let's start with Bill. He does the following analysis. Okay, so he says, all right, Adam was performing a number of trials. He performed 12 trials, and he got 3 good results. And so my test statistic is the number of good results. Number of good results, which I'll call little n. Okay, and I know under the null hypothesis how to calculate the probability of getting any particular value of n. So the probability of getting a number of successes out of 12 trials, conditional on the null hypothesis, is 12 choose n times 0.5 to the n times 0.5 to the 12 minus n. Okay, that's just the binomial distribution thing about number of possible sequences with n successes. It happens in this case that our null hypothesis makes them a coin flip. So actually these probabilities are the same, and we can combine them into one expression, 0.5 to the 12th. Okay. I'm interested in testing the assumption or the claim that good results are less likely than a half. So my extreme values of n are going to be the small values. Okay, those are the ones that I'm kind of most interested in, where I get a small number of successes. And the probability of, let's say, something at least as extreme as what I did observe, which was n equals 3. Okay, what is that probability? Well, it's the probability of getting an n of what I got, which was 3, plus the probability of getting n equals 2, plus probability of 1, plus 0. Okay, so if I write those out, I get 12 choose 0, plus 12 choose 1, plus 12 choose 2, plus 12 choose 3. All of those things are going to be multiplied by the same common factor, which is 0.5 to the 12th power. Okay, and if I then do that calculation out, I get the number 0.073, or about 7.3%. Okay, so at the end of the day, if I'm testing things at the 5% significance level, I'd say this is not a statistically significant result. It is suggestive, I got less than half by a good margin, but not quite a small enough number that I can conclude at the 5% level that I reject the null hypothesis. So I can't publish my result. I got to go back, collect some more data, try something else, go back to the drawing board. Okay, so that's Bill's analysis. Charlotte takes a different point of view. Okay, so Charlotte says, I know what Adam was doing in the lab, and I think that his procedure was actually that he was going to keep doing the experiment until he got 3 good results, right? And it just, might have taken 12 trials, it might have taken more than 12 trials. Okay, we don't know. But the thing that was kind of constant was actually how many good results he was going to get. And maybe this is, to do with the setup of the experiment, so maybe it's like each time there's a good result, that means filling up some container with, with something, and there are only 3 containers in the lab, and so, necessarily the kind of most data you could get is 3 good results, and we believe that Adam's going to kind of keep going until that end state. Okay, so this is Charlotte's interpretation of what Adam was doing in the experiment, and it's consistent with the fact that the last trial in his sequence was a good result. Okay, so that's maybe what's suggestive here, that it's not just that we got 12 trials, it's actually the last one's good, and we think, okay, that might indicate that actually Adam was going to keep going until he got that 3rd good result. Okay, so for Charlotte, the question is not how many successes was he going to get, but how many trials. Okay, so Charlotte is going to say actually what was random in this experiment was the number of trials, which I'll call capital N. Okay, and we can go through some more kind of line of reasoning. So the probability of requiring N trials to get 3 good results, conditional on the assumption that each one is just a coin flip, actually works out to be n minus 1 choose 2 times this same number, 0.5 to the nth power. That's right. Okay, and the reason why it's this n minus 1 choose 2 thing is that basically we imagine we do some sequence of n minus 1 trials, but we only get 2 successes in that trial, so we have kind of n minus 1 choose 2 times 0.5 to the n minus 1, and then we assume that on the very next trial we got a success and we terminate the experiment. Okay, so this is just kind of the probability of all of those possible sequences that terminate with a good result and that go a total of n. All right, so you can think that through on your own. So now again for Charlotte, the extreme numbers, okay, are not going to be the ones where the number of successes is small, but where the number of trials to get 3 successes is a large number. Okay, so we're interested in situations where the probability of getting a good result is small, and that occurs if we need a lot of trials to get 3 good results. And so the thing that's going to cause Charlotte to reject this null hypothesis is if she sees a very large n. Okay, so the probability of getting something as extreme or more extreme than this particular realized value of n equals 12, okay, so ordinary orthodox argument. What's that probability? Well, that's the probability that n is at least 12, which is, under the null hypothesis. I should specify. That's here too. That's 1 minus the probability of taking less than or equal to 11 to get the 3 trials, which we can write out if we just kind of sum up this series. So it's going to be 1 minus something like, okay, probability of taking 11 is going to be a 10 choose 2, 0.5 to the 11th, plus probability of getting, of requiring 10, et cetera, et cetera. So it's going to go all the way down to 2 choose 2, which is 1, 0.5 to the 3rd power. Okay, that's the kind of shortest possible sequence where we just got 3 successes in a row. That could have happened. Okay, now all of those are the cases we want to exclude. We add those up and we take 1 minus it, right? And this now is then the probability of getting a more extreme result, meaning more trials. And that works out to be 0.0327, or about 3.27%. Okay, so what's interesting is that they get to different numbers. Okay, so Bill does his analysis, gets the number 7.3%, says, darn it, not significant enough to publish, doesn't meet the 5% threshold criterion. Charlotte, according to her assumptions, says, no, actually it is significant, right? The probability is less than 5%, meaning that it's in the rejection region that I've defined of values being greater than 12, right? So which is it? Is it a significant result or is it not a significant result? And it basically seems to hinge on their different understandings of what was going on in Adam's mind when he performed the experiment and what the conditions were for terminating the experiment. Okay, so it comes back to this question in the orthodox framework of not only what data did we get, but what other data might we have gotten that we did not get, and what are the probabilities that we would associate with those things. Okay, now it's interesting to note, both of these people agree on the calculation of the probability of the actual data. Right? The thing that they disagree on is what other data they could have observed. In the Bayesian program, this is the only thing that matters because we don't care about what fictional data we could have gotten but didn't get. And so the fact that we can compute the likelihood of this data under the null hypothesis is all we're going to need to assign posterior probabilities to the hypothesis if we also have the prior. Okay, so our approach would be very different and would not involve any of this business of, what kind of terminating condition was Adam using when he performed the experiment. In particular, let me just write this over here. In the Bayesian program, whatever probability, let's say, we want to assign to the hypothesis conditional on the data, okay, we can write that just as easily as the probability conditional on the data and some summary statistic of the data. Okay, so as long as this number we pick is consistent with what we actually observed, meaning number of trials or number of successes or whatever it is, this logical conjunction, logical combination of the data and its statistic being true is the same as the data being true because we learn that from the data. And so there's no difference here in this conditioning information, so we must arrive at the same posterior probability assignments and the same acceptance or rejection of the hypothesis. Okay, so basically for Bayesian inference, it doesn't matter. You could throw into the conditioning information the idea that the tests we're going to run, the trials we're going to run until some number of successes was reached, or until some number of trials was reached, or until some ratio of the successes to the number of trials was reached, or any other kind of summary quantity of the data, right? You can condition on it because actually from that data you learn everything. And the whole question is going to be, okay, how likely is the data? In fact, we could just look at kind of a videotape of someone performing the experiment and we'd reach the same conclusions as these other people after having done some lengthy interrogation of the person doing the experiment and making their conclusions based on what they think was going on in his mind when he decided to stop. Okay, so this is really, again, the kind of advantage of the Bayesian program, is that actually in some sense we're more objective here because we don't include in our analysis any assumptions on the state of mind of the person performing the experiment the way that the orthodoxians would require. Okay. So that's basically some of the issues with hypothesis testing in the orthodox framework and where we can get kind of silly results that for Bayesian analysis wouldn't be a problem. Let's then think about specifically more questions about parameter estimation, and in particular this notion of an unbiased parameter estimate. Okay, so last time we talked a little bit about this in the context of drawing balls from an urn. Okay, and the idea was we have some parameter, right? You can think of that as just the value of some constant that is unknown to us, that in some way plays a role in the sampling distribution of the data. Okay, so maybe it's the fraction of black balls in an urn or whatever it is. Okay, some constant that's unknown to us, and we want to estimate it. Okay, so according to the orthodox procedure, we can only do that via numbers that we can derive from the data and asking questions about the distributions of those numbers. Okay, these random variables called estimators. Okay, so we're going to define what's called an estimator, which will be, again, a random variable, so some summary quantity of the data, an estimator as an estimate of, let's say, an unknown parameter, which will be called theta. Okay, so the example that we talked about last time was where theta was the proportion of balls in an urn. Okay. One of the kind of nice properties that orthodox statistics will usually require of these estimators is that they should be what's called unbiased. Okay, so we say that this estimator is unbiased if it happens that the expected value of f, conditional on whatever value of theta is the value theta. Okay, so this E bracket notation, this means the average, okay, so this expected value, which means the average of this random variable f. Okay, so f depends on the data, so it's random in the orthodox framework, meaning that it gets a probability assignment to it, or it gets a probability distribution assignment to it. If we take the average of that value over its probability distribution, we can ask the question, all right, in that probability distribution, there's going to be some parameter, right, this unknown constant that is kind of fixed even though we don't know what value it is. If it happens that no matter what value we choose for it, when we do that calculation of the average of f over its distribution, we get the number theta, then we say that this is an unbiased estimator. Okay, so again, the example we talked about last time with the urn drawing, what we were going to take as our estimator was the sample mean. Okay, and we can generalize that a little bit. So let's say that we have a population, okay, a population of people. Each person has a number just associated to them, and let's say it's something like, I don't know, the average height. Okay, so the number is h for each person. Or sorry, the number is the height. Okay, and the question we're going to be asking is, what is the average of this number h over the population? Okay, so we just like to know what's the average height of all the people in the population we're talking about. And when we talk about averages over the population, we'll use the symbol angled bracket. Okay, so this means average over the population, and that's our parameter theta that we're interested in estimating. Okay, so we assume that we do that by drawing a random sample, okay, by whatever means we do a random sampling, and let's say that our values we get of the n people we sample in the random subset are x1 through xn. Okay, so what we'll then say is, let's define what's called our sample mean, okay, which we'll write x bar as the average of these x values, and the average is just 1 over n times the sum I equals 1 to n of xi. Okay, so this is what's called the sample mean. And the important thing to remember here is that it depends on our data. It's a function of our data. So it is random, just as random as the sample is, and therefore it has probabilities associated to it. It can take different values for different samples, and we can ask questions about its probability distribution. Okay, it happens then that this statistic, this random variable, is an unbiased estimator of this population parameter. Okay, so the expected value of x bar, given whatever the population average is, theta, will work out to be theta. And you can see that by writing it in terms of the expected value of this sum, okay, conditional on theta. And I know we haven't talked about all the mathematical properties of this, so I'm kind of assuming that you know a little bit about it, or you can just kind of believe me. This expected value operator is what's called linear, meaning that it distributes over sums. So we have an expected value and average of a sum, so the average of the sum is going to be the sum of the averages, and we can pull out this constant 1 over n. That's another property of it being linear. So this is going to be the sum of the expected values of these xi numbers. Okay, now I'm taking the sum over the sample. And now we just have to think about each one of these individually. Okay, so remember our assumption was that these population members are drawn at random from the population. The population has a distribution of heights or whatever it is with an average value of theta. Okay, so it's probably not too hard to believe that by definition, the expected value of that single random draw, the average value over its distribution, is theta. In fact, its distribution is exactly just the kind of summary distribution in the population, and so these things are equal by definition. So this is the sum, I equals 1 to n. For each one of these is going to be theta. So we have n thetas, and we have 1 over n out in front. So we have 1 over n times theta, in other words, theta. Okay, so may seem like a kind of circuitous way to get there, but actually there's some content to this, and what we're saying is that from our data sample, if we take the sample mean, which is a random variable, its expected value over now its sampling distribution is the population average. Okay, the average over the whole population. Not too surprising, but a little bit non-trivial. Okay. And the question is, all right, what about maybe other quantities in the population that we might be interested in? So instead of wondering about just the average, let's say, height in the population, we might want to know, okay, how spread out are the heights? Okay, so what about, let's say this number, usually called mu2, which is defined to be the population average of the squared deviation from the mean over the population. Okay, so that's like h minus this population average number squared. And again, this angle bracket notation means average over the population, but now I know how much do people deviate from that average in the sense of squared differences on average. Okay, so again, a little bit hard to say in a short description, but we can actually write that out. Okay, so what we'll say is that that's, let's do it this way, it's h minus the average of h squared, which we can write as h squared minus 2h h bracket plus h bracket squared bracket. Again, with averaging over the population, we have the same linearity properties that we have with the expected value operator. Okay, I may just have to take my word for that, but it's the same kind of averaging just over a different distribution. If we break up this sum then into 3 parts, we're going to have the average of h squared. We can pull this number out because this is actually just a constant, so we have 2 bracket of h, and what's left inside is the bracket of h, and then we have again another constant bracket of h squared. This number is the average of h squared. We have 1 of them here minus 2 of them there, so we get in the end average of h squared minus the average of h as a number squared. Okay, so that's just another way of computing what's called the the population variance, or second central moment of the population distribution. Okay. And let's just go ahead and assume, maybe for the sake of the example, that the population average is 0. Okay, so we're talking about deviations away from 0, and we've just done some change of scale to make the mean value 0. So the question is, how are we going to estimate this thing? So I'm going to put a box around this. And what is kind of suggested here by this, doing the calculation this way, is that maybe we can get at it with some kind of similar thing with our data sample, the way that we did with theta. Okay, so what we're going to guess is an estimator, which we'll call little m2, which is defined to be the average in the sample now of the x squared terms minus the square of the average in the sample. Okay, these sums are from I equals 1 to n, xi, and we take the square. Okay, so hopefully you can kind of see the correspondence there, right? So the number we're estimating, we actually can compute in terms of the averages over the population of squared terms and then taking the average squared. So we'll just say, all right, we'll do the same thing for the sample, right, where we take averages in the sample of squared terms and then subtract the square of the average in the sample. And our guess is that maybe that's a decent estimator of this population squared difference average. Okay, let's see how that shakes out. Okay, so this is, by the way, this is the first part of chapter 17. I think it's sections 17.1 and 2. All right. If we define this estimator this way, and ask the question now, okay, what is its expected value conditional on, this unknown parameter, which is the population spread. Okay, so this is our estimator for the thing. We want to know basically how biased is it. Okay, so let's take its expected value now as a random variable that is random over the sample. Okay, now what does that work out to be? Well, it's the expected value of these two things. We're going to break that up in terms of the sum of the expected values. So we'll have 1 over n times, let's just do it this way, expected value of the sum of squares, which is going to be the sum of the expected values of the squares, xi squareds. Okay. Then we have a minus the expected value of this thing, and we're going to basically take this 1 over n as a constant squared out of that expression. So we're going to have minus 1 over n squared, expected value of the sum of xi, whole thing squared. So hopefully you can see that logical operation, right? We're taking expected value of this whole thing, but we expand out the product and just bring the 1 over n squared out as a constant. Okay. This first term we know actually how to compute because we made an assumption that the population mean is 0, and so the expected value of the square of a randomly chosen number is just the population square average. Right? So that's the population say height squared, which is by definition mu2. So this is going to be 1 over n. We have a sum of n of these guys, and each one of them is going to be a mu2, okay, in the sum. Then we have 1 over n squared factor. If we expand out this sum squared, right, we'll have products like x1 squared, and x2 squared, and etc. Well, then we also have cross terms like x1, x2, and x2, x3, etc. So basically, this is going to be a sum over all possible I and j, 1 less than I less than n, 1 less than j less than n, of products like xi, xj. Okay, and now we just have to think about what are the expected values of each one of those products. Okay, so some of them are going to be squared terms where these are equal to each other, so we'll have like x1 squared and x2 squared. Some of them are going to be cross terms, like expected value of, let's say, x1, x2, right? Because of the assumption that these population members are drawn independently, so again, we're making a little bit of an approximation, but let's just say that we do the sample with replacement, or we do it without replacement, but we approximate it as a with replacement problem. So the assumption is that their values are independent on these random draws. This expected value is just a product of the expected values. Okay, again, this is a property of the expected value for independent variables, which we haven't really gotten into that much. By assumption, each one of these things has an average value of 0, so that's going to be 0. Okay, so we made a change of scale so that the population average, meaning the expected value of any single sample of this variable, was 0. And so when we multiply these two things together, they're going to be 0 whenever we have cross terms with different indices. Okay, so in the end, what we get is we have 1 over n times mu2, so that's a mu2. And then we have a minus 1 over n squared. And inside this expected value then, we have the sum of expected values of just the squared terms, that's all that's left. Okay, which is the same mu2 that it was before. Okay, so that's mu2, 1 over n squared. We have n of them, and each one is mu2. So we get mu2 times 1 minus 1 over n. Right, the n cancels here. We have 1 over n times mu2. 1 minus 1 over n is the same as n minus 1 over n. So this is our final answer. Okay? Sorry, so I made that mu look a little bit like an m, but let's change this. It's a mu to population second central moment. If we define the sample estimator the same way, we end up with an expected value of that estimator being equal to the population number times this small constant, times this kind of correction factor. Okay, and what this correction factor means is that this is not an unbiased estimator of the population parameter, right? If we take the average of this value over its distribution, we do not get mu2, we get mu2 times something that's not quite 1. Okay, for this reason, people will usually, in the kind of standard statistics textbooks, actually say, okay, we won't use that estimator. What we'll use instead is, let's say, something called capital M2, which we'll define to be n over n minus 1 times this little m2. So basically, wherever we had a 1 over n in the calculation of m2, we'll take that out and put a 1 over n minus 1. Okay, and if you've ever taken a statistics class or you've read a statistics textbook and you've wondered, why is there this 1 over n minus 1 in sample variance calculations or sample standard deviation calculations? This is why. Okay, because what this means is that the expected value of m2 conditional on mu2 cancels this correction factor, and we get that m2 is an unbiased estimator. Okay, so that's already kind of silly when you think about how it's used, because actually what people usually do is take the square root of this thing, right? So instead of taking the average squared deviation from the mean, people usually take the square root of that average, called the population standard deviation, okay? And what they'll try to estimate it by is something like the sample standard deviation, which they'll define as the square root of this thing, right? And so the thought process is, well, if its square is an unbiased estimator of the square of the thing we're interested in, then that kind of makes it good. We can take the square root of it. Unfortunately, this property of being unbiased does not satisfy that. It doesn't translate over from one variable to the next. So when you do a change of variables or you do a transformation, the transformation of an unbiased estimator is usually not an unbiased estimator of the transform parameter. They don't commute. So it's a little bit weird already that people define sample standard deviation in terms of the thing that if you squared it would be an unbiased estimator of the square of the thing that you care about. But as Jaynes describes, it really kind of comes back to the question, why do we care about this unbiasedness sort of at all? Where is this coming from? And why should it matter that estimators are unbiased? And what he suggests is that actually another way of thinking about the kind of accuracy of an estimator of a parameter would be to look at something like what's called the mean squared error. Okay, so if instead of just asking how close is the average of the estimator to theta, you might ask, okay, how close is it? How much does it deviate in squared terms from theta on average? Okay, so another measure of how concentrated the distribution is around the true value theta, probably by orthodox standards at least, that's a more important criterion for the quality of the estimator than just what its average is. Okay, so I won't go through the whole derivation, but basically what you can do is take this expression and break it up into two parts, one of which is the bias. So let me write that here. So estimator, expected value of f minus theta. Okay, that term comes in as a square. And then the other term is the expected value of f squared minus its expected value squared. Okay, so basically the variance of the estimator over its sampling distribution. Okay, this is what's called the variance of f. Okay, so basically how spread out it is over its own sampling distribution. And then another term which is the bias, meaning how much does it deviate from the true population parameter or true parameter value, whatever it is, that number squared. And so the point of kind of writing it out this way is that actually you can see where maybe choosing a different estimator to remove the bias, like we did here, right? Changing f so that this term drops out might actually not be so good if it increases this term, right? So if it makes for an estimator that has a higher variance, right, then in mean squared error terms, we end up maybe at the same place or even worse. Right? So however much we reduce this by, we might increase this by. And if you think in terms of geometry, this is basically saying there's some component of the mean squared error that is in the direction of the bias and then some component that's orthogonal to it. And there's no real reason we should prefer one over the other. We really just want in the end something that is kind of close to it, okay, in mean squared error terms. And he does a kind of lengthy analysis of this and looks at other possible estimators that you might use for a population standard deviation, okay, which I won't go through, but in particular for a normally distributed population, he finds an estimator, okay, with a mean squared error for 100 samples that's equal to the mean squared error for the orthodox estimator for, I believe it's n equals 203. So basically, because of this trade-off that we have available between bias and variance in terms of the mean squared error, we can optimize this in some sense and actually find an estimator with a smaller mean squared error, or equivalently, the same mean squared error for a smaller n. And the way that you can then think about this is that by using the kind of standard orthodox estimator that's unbiased, if what we actually cared about was mean squared error at the end of the day, we've effectively thrown away about half of our data set. Right? We've made such inefficient use of the data that it's as though we only had about half of it, which if the data is very hard to come by and it's a very expensive experiment or survey sample or whatever it is you're doing, that could be a very significant difference, right? It could basically be saying to get the same results, you need to collect twice as much data. It's going to be twice as expensive. Okay, and it's all just comes back to this idea that actually biased estimators may be better when measured by some other criterion. Okay, so the last thing then that I thought was interesting to ask is just why is it that we persist in using unbiased estimators when, by other numerical criteria, they are actually not as good, and they may be making kind of less efficient use of the data that we collect. And what Jaynes describes as, I think, quite interesting is that basically statisticians have this habit of using names for things that have a kind of normative character to them. So they seem to embed kind of value judgments about whether something is good or bad. And if you read through kind of all of the standard statistical topics, you'll see a lot of this. Okay, so you'll see things like unbiased estimator, efficient estimator, consistent estimator, uniformly most powerful test. There's one called best linear unbiased estimator. Okay, so basically they use words that seem to have good and bad value judgments in them. And I think what Jaynes kind of hints at is that maybe this came about because of the conflicts in the schools of thought in statistics, around, let's say, the early 20th century, when you had different camps trying to kind of establish their superiority, and they were all going to give names to their little tools and their kind of procedures that made them sound like the right ones. Okay, so if you were then a scientist and you were trying to decide on, which technique should you use, of course you're going to gravitate to the one that says it's the unbiased one because no one wants bias, that's a bad thing. Or you're going to try to use the one that's efficient because efficiency sounds like a good thing, or whatever it is. So you're going to basically be led by this advertising of the names of the estimators and the techniques, one way or the other. Now there's obvious examples where that's going to get you into trouble. This is one where actually using an unbiased estimator is like throwing away half your data. Jaynes gives another example of like estimating, let's say, the width of San Francisco Bay for the purpose of laying a telephone cable across it. Okay, so if you had some procedure to do that estimate, it's then obviously the case that you'd want to err on the side of having a biased estimator too high, because if you overestimate the true width of the bay for laying this cable, then you'll use too much cable and it'll cost a little bit more than you maybe could have gotten away with. If you underestimate, then you'll get to the end and your cable won't stretch all the way, and you'll have to start over or do some very expensive thing to remedy the situation. Okay, so this kind of gets into what Jaynes calls decision theory, which is going to be chapter 13. And basically the question is, all right, we don't really care about bias or anything. What we care about is what are the consequences of making decisions based on the probability assignments we make to whatever unknown parameter we're interested in. Okay, so that's one kind of simple example of it. What Jaynes says about why people continue using unbiased estimators is that actually even after you demonstrate that they are worse, people will continue using them because, as he says, statisticians are caught in a psychosemantic trap of their own making, right? So they kind of can't get away from these things that they've associated these normative words to, because they're just so suggestive that they're the good ones and you don't want to use the bad ones. Okay, so thinking of this in terms of bias is actually kind of dangerous professionally. And in the Jaynesian program, all of these things, these questions about what are the right estimators to use and what are the qualities that make an estimator good or bad, all of those things drop away because they're all kind of symptoms of the larger problem that we don't have a consistent unifying logic for how we should be doing this parameter estimation or hypothesis testing from the beginning, right? So in the Bayesian program, we don't have this issue. We don't have to pick an estimator ahead of time. We don't care about what other data we might have gotten but didn't get. We don't have to worry about things like optional stopping and these other kind of weird, absurd little situations, because we have one logical rule, Bayes' rule, or the product rule of probability, that allows us to do consistent inference based on whatever data we do observe. And that's going to apply for all problems and for all situations. All of these estimators are going to be available to us if we need them, and if we don't need them, we're just going to discard them. Okay, so that's going to be basically what we'll see in the remainder of the program that Jaynes lays out for doing the Bayesian version of these parameter estimation or hypothesis testing.